Kevin, hey, how are you?
All good.
Good to see you. Strangely enough, after all of these weeks into the quarter, I think this is the first time I'm seeing you.
It
So
is. Yeah, it's
yeah,
good to finally
I've
be
been
able
to
to
a
talk to you in
couple of
person.
meetings, but you couldn't make it because you're working full time. So
Yeah. Well, it's
great.
good to see you finally.
Yeah, likewise. Anyway, I'm glad you're doing this. So I explained the intuition behind this, and you kind of see where the high level plan is, really, isn't it? Because if it's a peak distribution, you expect Splay to do better. So I think here's where it got left off with Riley and Walter, because they started working on it. I don't know, maybe week 9 or 10 or something. I think I forget. They didn't have any time, so
Okay.
they put this together. All right. So here's what I think they did. Um, so when you get to a really peaked distribution in Splay like this, standard deviation really close to I don't know, maybe 1 or something like that.
Okay.
It was very hard for them to even encounter the other data in the stream. So the limit, the impulse in the limit is just going to deliver 1 element perpetually. Yes.
Right. Right.
So the tree is always 1 element big, and so they didn't have any basis for doing a comparison, because AVL tree had 1 million nodes in it or 500,000 nodes in it. And so, even if it was logarithmic, you'd say, 2 to the 10, 2 to the 20, right? So you'll say, well, it's gonna go 20 levels deep, or 10 levels deep on average.
Okay.
To find an element on AVL, but Splay is always going to get, but we can compare because this is a big tree and that's a tree of 1 element. It's like O of 1 axis. So they tried to increase the sigma, but even when they increased the sigma, the trees were not, the Splay tree was not growing big enough to be able to be compared with an AVL, because AVL was always getting fed uniform data. It had all of the 500,000 elements in there. But the Splay, because of the peak data, was not encountering a huge majority of the 500,000 elements. And so Riley was, trying to fiddle with this, and he came up with lots and lots of ideas, I think. And I don't think any of them worked. And one, he wanted to normalize the tree sizes somehow. I don't know. So we've got to figure out some way of figuring out. So the reason this was also confused, the puzzling, was that whatever numbers we could figure out, I think, seemed to suggest that AVL is always beating the pants off the Splay tree, right? It doesn't matter what the standard deviation is. And so before throwing in the towel I said, I was thinking, well, I don't know, maybe that's what it is. Maybe it's because the hardware level optimizations are so good these days that read-only access beats the pants off read-write access. Because Splay is always read-write access, and AVL is only read-only, right?
Okay.
It's all constant. And so coming up with wild ass theories like this and saying, well, maybe that's what it is, but I don't know, there's a flaw in the experiment, maybe that's where we're trying to explain bad, experimental data. So I thought that you might be a good person, if you're interested in it, to look at it and say, wait, what the hell is going on? Because you seem to have the right kind of questions for these kinds of things in data structures. Why is it? Because, our whole premise of using Splay trees is better when there's a modal distribution, because there's a whole bunch of items that will get accessed. So maybe I'm thinking, all right, so there's a bunch of items, and then they're all only 5 levels deep in the tree, 2 to the 5, 32 items or something like that, or even 10 levels deep. Whereas AVL has to go on average 15 levels, and Splay only has to go 10 levels.
Okay.
Yeah, I don't know. Maybe but as the distribution gets peaked more and more, Splay should win. And I think the challenge really is making sure that as you peak the distribution, the trees remain sufficiently comparable. Like this doesn't shrink to a 1 node tree, and that one continues to be a 1,000,000 node tree. So that's, I think, where we left it. We're trying to brainstorm ideas and say, well, maybe just pre-populate both trees with 1 count of all elements. Yeah, and then start doing this. But even then, you're just approximating a peak distribution with a uniform plus a peak distribution. Yeah. So I don't know what way. So we have to come up with ways in which you can design this.
Okay. Yeah, it's definitely a lot more than I realized, which is interesting. Riley shared with me his like I guess GitHub, but the explanation on it was very brief. I didn't realize he had already been through so many, I guess, like iterations of
Did he share
experiments.
the code? Did he share his code with you on Git?
Yeah, I saw the code. I've mostly just looked at the his like splay tree and AVL tree and some of the just a couple of the experiments he ran. Um in the actual like I guess the like the README page on his GitHub, it just he made it sound like in his experiments he just filled the trees with like random numbers and then made like I guess an array of like find numbers that he was going to search for, and he like made the find numbers that he was going to search for, he had those follow like a normal distribution with a given standard deviation.
Yeah. So I think that's what I was remembering. So he was pre-populating both trees with a lot of these numbers, so that all of both trees were the same size to start with, and then he was hitting the splay tree with a peak to distribution, and the other tree was hitting with a uniform distribution. But the math of it doesn't quite work out properly because the distributions are different, like you pointed out, right? So was it an email, or I don't know, you pointed out. So if the distribution is different, then it doesn't really make sense so we've got to so it's up to you 100%. And technically you don't have to do this, okay? You don't have to do this for credit or shit like that. I'm just I'm passing it on, not passing it on, I'm passing on this nugget of an idea to you because I think that this is up your alley, right? This is something that you would be inherently curious about because you're interested about data structures, and why is we can actually make that faster, and by doing this little thing and so on and so forth. You're interested in this CPU cycles and how to squeeze things out of maximize the efficiency of machines, essentially, right? And so I thought this might be up your alley. If you're interested, you can do this. Any help I can offer, I'm happy to offer. And hopefully it'll turn into a really nice little report you can put on Stack Overflow, because I'm pretty sure lots of people out there might be interested, right? Maybe it is the hardware technology has evolved so much that AVL just is much better than Splay altogether. Who knows? Right? Because I think the other thing that you mentioned was also to do with the quick sort. Maybe that thing, stack optimizations and recursive calls. Things have changed. Yeah, library code doesn't change as much as the driving technology usually. The library code usually follows because library code is working code, and they don't make any hardware changes that's going to break existing systems. Yes. So hardware changes are always backward compatible. And so library code is, usually you have the luxury of laziness. So you can sit with the, hardware, you can let it do slightly inefficient stuff until people start noticing. And then you can go and, take advantage of all the latest hardware, because hardware keeps changing all the time. But software has a cycle. That's what I think. I don't know. But it's worth finding out. I think lots of people will be interested. I was very interested. I couldn't find anything on Stack Overflow. So I just but I didn't do an exhaustive search like a PhD and all, right? So I just did a search, a trivial search, and I couldn't find any data on this. But I think it'll be interesting if you're interested, and hopefully you'll get something out of it. Yeah. So I don't think you have anything to worry about this class, by the way. So I think you're good so far. So you do okay in the finals, I'm pretty sure. So I think you're good. So you can use the rest of the time to just noodle on this, maybe do a report and get something out of this for yourself on Stack Overflow, right? You don't have to credit the class or anything. You can say, well, this came out of a discussion I had with my fellow programmers, something like that. That's fine too.
Yeah, no, that'd be awesome. It's definitely something I want to see if I can move forward for sure.
Yeah, don't feel obliged. So I just want to toss it up in the air to see if it strikes your fancy. That's all.
Okay. So I guess one question I have is with the standard deviation, so we're trying to find the standard deviation where I guess like so initially like a splay tree should outperform the AVL tree while the standard deviation is small, and eventually it'll like hit a point where
Yeah. When
with
the
it,
standard deviation is small, you'll only encounter a small set of data, and so the
right,
splay should. And we can show it theoretically too, right? Theoretically also, if the standard deviation has an impulse, you know, if zero, you get an impulse. So it has, this display has to have O of 1 performance there. Because no matter where the element is, when the impulse happens, that's going to get rotated to the root. And that's the only element is ever going to be accessed after that, right? Because, you know, because of the impulse, all of the elements on this side and that side won't get touched at all.
right.
So so it's O of 1. So we know for sure that at the, you know, right extreme, we got splay as a clear winner, theoretically proven. And at the left extreme, we have, you know, AVL, because it's you know, I don't know whether it's AVL, right? On the left extreme is basically log n both times, you know, because a splay or a more class is also going to be log n.
Right.
So I would expect that both start off like this, and then as the standard deviation decreases, splay starts getting better. And because we know for sure that, you know, when the standard deviation is 0, splay is going to kick ass, like, you know, it's O of 1 axis.
Right.
So it's up there. And, you know, it's going to be at with uniform, it can do better than AVL. So it's got to be locked here. So there's some change that happens from here to there. As the standard deviation changes, it's jumping. You can't just jump like that, right? It's got to do something. It's got a continuous curve. And so I think that shape of that curve is probably an interesting one.
Okay.
There is the library function. Because you looked at the AVL and the splay code, you probably didn't look at the main code. The main code is where they use the library. There's this very simple library called, it's a library's random number generator. And it's an object, it's a class, you instantiate it, and you tell it, I want randoms, I want a Gaussian, you know, normally distributed random. This is the mean, and that's the standard deviation, and it'll just spit out numbers in that in that range. So you can say the minimum of the, you know, I think for normal, you just say the standard deviation and the mean.
Yeah. I think I looked it up on like the CPP reference.
Oh, I see.
website.
I see. Okay. Yeah.
Yeah. I think you just provided a mean and a standard deviation.
That's all. So it does. So it goes from max int to min int or something like that, or max float to min float or something.
After you provided the
range, you have to give the range also, do you?
I don't know if you have to give it a range. I know that like it just kind of generates.
Yeah, that's what I thought. Because a Gaussian doesn't have any range, right? It's minus infinity to plus infinity.
Yeah, it's like it's like 99% of everything will be in a range, but like a very small can be outside the range.
I think those are the interesting parts. Yeah, if you do this experiment, is to noodle on those and say, well, you know what, these are the ways in which we can compensate for it mathematically, or, you know, code wise, or, you know, in the model, in the experimental setup, to set up a control for that changing, right? So those are the interesting parts that would make this fun, I think. Anyway, yeah, just something for you to think about.
Okay. So with running the experiments, so they're mostly just using, I guess, like a search function, like they're just measuring the amount of time for define an element in each tree. Okay.
They're doing 1 million calls and averaging or something like that.
Okay.
And I think for a single run, it does, maybe it does several million, and they keep it leave it running overnight and dumps a table in the morning or something like that, or a couple of hours, and then you get a tabulated result saying, well, I did 5 million calls, and this is a total for 5 million calls, and they divide by 5 million to get the average for one call.
Okay.
It's you know, the main code is less than, I don't know, less than 150 lines of code. C++.
Okay, yeah, I'll definitely have to have a look at that then. Okay. And the trees, when they're making the calls, are they filling the trees with the same like set of data?
Yes. So this is the original setup. In the I think in the original setup, what happened was that so they had an AVL tree, an empty AVL tree, and an empty Splay tree. Just give me 1 sec, okay? I'm just going to switch off this heater. I don't know where it comes from.
Okay, no worries.
You guys open the door a bit. That's better. Yeah. Okay. So this is the setup originally. Is I start off with an empty AVL tree, empty Splay tree, both
Okay.
empty. Now, I think there was a populating phase. So this was the first incorrect experiment in which they found that, Splay didn't grow at all. It's, right? So they set up a random number generator, and they say instantiated the object and said, now I want a Gaussian. They used this Gaussian both times, except in one case, the Gaussian had a standard deviation of infinity or maxent or something like that. So that the output of the Gaussian, even though they're using the exact same random generator, it's a Gaussian, but it's very flat.
Okay.
Because it's a huge standard deviation.
Yeah.
So they use the same Gaussian, and then the sigma varied from minus infinity to, I think, 0 or something like that. Oh, infinity to 0. So so they kept changing, and so that basically took the distribution all the way from uniform, very flat, to a peak distribution.
Okay.
And so for each one of those sigmas, they generated, I think, 1 million numbers, 1 million randoms from the generator. And they stuck the 1 million randoms in the AVL tree. And then they used the seed function. The random number also has a seeding thing, so you can control it.
Okay.
So they reseeded it with the same control seed. So you get the exact same sequence of 1 million numbers again. And those 1 million numbers were stuck into the Splay tree. So exactly the same numbers, same sequence. And then after the two trees were built, they had the measuring loop. So in the measuring loop, they made, I don't know, a couple of million calls of random elements to the AVL tree. Some may be present, some may be absent, I don't know, right? Because you're just picking up random elements in the range and asking, oh, is it there, right? So maybe they did a couple of million. And so they found the average find time on AVL by dividing a couple of million by the total time by a couple of million. That's the average find time for AVL, and they repeated the exact same for Splay with the same standard deviation. So elements coming in, and you got a Splay, and you basically find and contains, right? So you do contain, do contain. And they took the measurement. It was the average find time with Splay was X seconds. The average find time with AVL was Y seconds. And they changed it. Now they changed the sigma, not negative 9,000 anymore, negative 8,000 or something like that. Repeated the whole experiment. So as the sigma started moving towards 0, they expected that the Splay time would start getting better and better.
Right.
Which actually did. It actually did. But I think it was because the Splay tree was getting scrunched up really, really fast. It wasn't even seeing most of the data. The tree was getting smaller. And then I when they described it to me, I remember that I theorized hypothesis anyway, saying that, well, it's probably because Splay find involves read-write operations, because you're going to be manipulating, shuffling things around. Whereas AVL find, there's no write operations at all. It just has to read.
Right.
So there's no relinking pointers and stuff. And maybe that is what is killing Splay, but we never found out. Because we don't know if there's a flaw in the experiment, by the way, actually. So he didn't have time to think.
That was gonna be one of my questions, was like on the every single find, like were they letting the find like change the Splay tree, and then on the next find use the new updated Splay tree, or were they keeping like the original?
No. Splay. It's got to be a proper. Otherwise, if it's a small standard deviation, the bunch of elements won't get rotated to the top.
Okay.
They were always doing this splay, the proper splay, proper splay,
Okay.
and then finding that, well, it's not giving the win they expected.
Okay. And
Yeah.
the numbers they were finding for, or that they were trying to find, so each one of those random numbers, was it a random number that was like in the tree, so it was always being
No,
found,
no, no.
or
So,
were okay, some were
basically, you have. I think that my recollection of I haven't seen. But, I mean, I saw it, but I don't remember all of it. So they have a distribution, right? They have a distribution spanning, I don't know, from negative. I think you have to set the range in when you right. So I think they set the distribution as -1,000,000 to +1,000,000. No,
okay.
I mean, I think it was all positive, maybe 0 to 1,000,000, whatever it is. So they got a range. They got a range, and all they did was set the seed and draw 1,000,000 numbers from the range. That's a tree.
Okay.
And the same thing for find also. Set the seed, and then, but not the same seed. It'll be a different seed. But it'll be
Okay.
the same seed for, the Splay and AVL. They'll share the tree, same seed. But this seed will not be the same as the seed that was used when stuffing the trees.
Okay.
Does it make sense?
Yeah. Okay. But so the find numbers, they still follow the same Gaussian distribution. Like they have the same
Yes.
mean and standard deviation as the
Yes.
okay. But okay, yeah, but some numbers will be found in the tree and some won't be.
Some won't be. Yeah.
Okay.
This is just to mimic the actual situation, if
Right.
that was a real distribution. And obviously that's why. Oh, and also they had to repeat it. I think they repeated it for, this is just one tree, and they repeated it 10 times for 10 different trees, 10 different random trees, and then average that. So there's a lot of averaging to compensate for the noise, because it could be, you could luck out with a particularly well-structured AVL tree or a particularly well-structured Splay tree. So they did the same experiment again with two fresh 1,000,000 node trees. And then, did 2,000,000 calls each and some, average. And again, two fresh trees, two new random seeds, two new random seeds, and so on. And so I think they repeated it. So the experiment was run over many trees. I think many tree sizes. I think it's all documented in main. If it's not documented in main, in comments, let me know. Okay, then
Okay.
I will be more than happy to walk through the main code with you, during a meeting like this, because I
Yeah.
think I'll remember as soon as I see the code. I think I'll remember what they were trying to do. So I'll say, oh, yeah, that's what they were trying to do, and with this, this is the averaging. Because I think there's three nested loops. One is over all possible sigmas, right? I think they chose about 20 sigma points from 0 to infinity, something like that.
Okay.
So one is over all sigmas. For each sigma, they took 10. For each sigma, they picked. They selected a random control seed and seeded the random number generator, and then generated 1,000,000 nodes to make the tree, and then seeded the random number generated with the same seed and generated 1,000,000 numbers to generate a Splay tree, both exactly the same. So at that point, you have an AVL tree and a Splay tree built with exactly the same 1,000,000 numbers.
Okay.
And then after that, they did a loop of, I don't know, 5,000,000 lookups or 10,000,000 lookups of random numbers drawn from the same distribution with a different seed. So it's not the same numbers that got inserted. Like you said, some will be found, some won't be found. And that was done, many million lookups and then averaged. And then also for the Splay side, many million and then averaged. Now, that's just one line for that sigma. You produced one data line for one tree. So now you change the seeds, create brand new trees again, and repeat the whole thing. So for each sigma, I think they produced 10 lines, 10 different trees, each of them saying, this is the average lookup time. So that, in the end, you can average the 10 and say, well, you know what, for 10 different trees, so you couldn't have lucked out on any one of those configurations. So 10 different trees and average numbers. So there was a lot of averaging going on there to collapse counts and control for things, noise. But that's what I remember. But if you find any of that not commented or confusing, I will be happy to go over the code with you.
Okay, yeah, I'll look at the main program more thoroughly, and I'll definitely let you know if there's anything that I need cleared up.
Great. It shouldn't be, like I said, it's probably 100 lines or 150 lines. It
Okay.
shouldn't take. But you take a look, and as your time permits. I know you're working and also.
Okay, yeah, no, it definitely sounds very interesting. I think in Riley's GitHub, he said that on the README in his results, he said that I think like the splay tree stopped outperforming the AVL once it got bigger than 5, like once the sigma got bigger than 5.
Yeah. I think that I remember now. Yeah. Okay. So the sigma was 5 when the range was like 1,000,000.
Yeah.
So that seems like, it's almost, so the display only works well if it's an impulse, essentially, because 5 sigma of 5 when the range is 1,000,000. Yeah, it's like an impulse. And he said, when anything more than 5, display just loses the edge. Right? But then and then said that, yeah, and I said, well, that is really it's not an exciting enough result. It probably shows that display cannot be used anywhere at all unless you have an impulse, in which case. Yeah, I remember that's what he said. Yeah, thank you. Yeah, that's exactly what he said to me.
Yeah, in the results, he at least just on the README page, it didn't mention the range, so it was hard to tell if 5 was good or not.
Yeah. The range was enormous. I think it was 1,000,000 to 1, 0 to 1,000,000, right?
Okay,
So it's a million numbers, and then it doesn't seem right to me. Somehow it seems there must have been some bug somewhere, which we never got a chance to dive into. But I'm pretty sure if there is, you'll probably find out much sooner, and get to the bottom of it.
Yeah, no, I'll have a look at it and run through it. I kind of have to like learn by making mistakes myself, so I might have to repeat a few of their mistakes before I'm able
totally. I totally,
progress.
yeah. But fortunately, I don't think any of this will take you a lot of time at all.
Okay.
Most of these you can just, I'm pretty sure you'll be fine.
Awesome.
I'm here too. Even if you want to offload some coding work and say, well, I want to run this experiment and I want to create this class or, do this main, can you write this for me? Just email me, okay? And I'll just email you a CPP file that I put together. Yeah, we can meet. So you can offload work to me, and, run ideas past me, anything. Is fine.
Okay, awesome. Yeah, no, I appreciate that for sure.
Great. Do you have any other questions?
I'm sure I will, like once I look at the main more thoroughly. But
well, it doesn't have to be about extra credit. If you have any other questions about the class too, I'm happy to answer them. Yeah, it's just like a one-on-one, right? It's it's just a regular one-on-one meeting. So if you have any questions, I can answer them, especially if it's going to help other people. But I will actually attend a meeting, this group meeting next week. All right, week 11. That's the last week we meet before the finals. I'll come to the meeting on Friday. So I'll say, farewell to the team, because there's no continuing course that you can do after CS2C with me. So this would be the last one. So I'll come to that meeting for sure.
okay,
certainly, I'm happy to meet with any of you. Anytime. Thanks for doing the course.
No, yeah, I appreciate it. I really the quests have definitely made me have to like think and problem solve a lot more than the previous two CS like the two like prerequisite courses for this one.
Right.
It was they're kind of addictive, really. I wasn't
You know,
expect.
I was also teaching, you know, the previous two courses that you mentioned. So I was teaching like that for a long time before 2019. So I just like what you said, you know, students would write not write, how would they submit it? Oh, they submit the CPP files to Canvas. Okay, so they'll create the CPP and H files and submit them to Canvas. Then I get a notification. And then honestly, it was too much of a bother for me to download all the code and compile it on my machine, because 99% of the time, most of the code won't compile. Even a student that compiles is submitting into Canvas, you can imagine, right? Most of the day it won't compile. So I got to look at the code. Then I got them to print out, just send me PDF files instead of CPP files, so that I can get it on my iPad and circle with my pen, Apple Pen, and say red ink, red ink, red ink. So I did do that. But even then, I felt, like you said, students can't get a taste of coding until they're forced to do it, So you gotta keep on doing this, and I think this kind of forces them. So that's kind of cool. Yeah, I'll offer CS2C. I'm offering it in spring, and certainly next spring also I'll offer one more time before I retire. So
Awesome. Yeah, I guess I haven't since I haven't been in any of the meetings yet, I haven't really been able to introduce myself that well yet, but yeah, I'm a mechanical engineer. Like I have a bachelor's in that, but I'm trying to go to grad school in I actually got into a program for like next fall in something that's more computational. So that's kind of like why I've been taking these courses, and I definitely like feel like since starting your course, I definitely feel like my knowledge has made a significant jump that I think will like be able to help me when I do go to return to school. Because obviously, like with the mechanical engineering background, that doesn't it's not going to help with the I guess graduate level computer science courses.
No, I think you'll be surprised. Really. Maybe you won't be surprised, because it does help a great deal. I think, in my opinion, because my background also was in engineering before coming to computer science. Okay. But I found that a lot of what I learned in engineering helped me, minimizing things. And engineering is all about efficiency and minimizing things. And because anyone, like I say to my 2A students, anyone can build a house, but an engineer can build an efficient house, using the least amount of resources.
Yeah.
And so we just figure out what the right things are. And so that kind of mindset, which engineering encourages, comes into play when you start building products, especially in computer science. And also that mindset, if you've got the engineering mindset, also helps in running companies, because you look for efficiency. And say, cut the fluff, and do these things and not waste things. And so I think the engineering mindset really helps in computer science. Scientific mindset generally helps, but engineering, because it is also targeted towards efficiency, I think. And say, we can do this, but we don't have to waste so much to do it. We can do it. And I think you have that eye to say, we don't have to waste carbon, essentially, right? Because if you have an inefficient program, you're just wasting carbon. Some computer out there is churning out you're using more electricity than it should. Yeah. Right. So I think that's where it's cool. Yeah, I think your engineering mindset will really, really come in useful. So I'm happy for you, and I hope to stay in touch with you and see where all the cool things that you'll be doing.
Yeah, of course. I'll definitely stay in touch even after the course is over.
Sure. Okay. All right. Thanks for making this meeting, and just feel free to let me know anything else. Right.
Yep. Awesome. Thank you. Yeah. Thanks for meeting with me so late.
Yeah. Pleasure to talk to you. Bye.
All right. See ya.